Okay, so we looked at the inheritance hierarchy. We looked at working with subclasses and superclasses. We talked about the super keyword. We had to look at some of the code in the tutorial slash practical lecture yesterday. And what we're going to look at today is looking at the next stage of working with advanced object orientation, and that is working with interfaces. So I'm not going to wait for this timer to go. You can find the code on Blackboard. So what we're going to have a look at is Java's way of handling the problem of multiple inheritance. Multiple inheritance you could do in C++, but there was a problem that was known as the diamond problem. Diamond problem existed when you had two parent classes that have a common grandparent. So you have this diamond shape in the hierarchy of inheritance. And that was the problem because when you have functionality that's defined in the grandparent class, that functionality is specialized in your parent classes. Which implementation does the child class now do? Does it do parent A or does it do parent B? Which order does it do it in? So there were ways around that. You could try and make it work, but it was an issue that is not clearly defined how to fix. So Java said, okay, we don't want to have this problem. We don't ever want to have a situation where we have the diamond situation, and we're going to avoid that completely by saying there's only single inheritance. So in Java, you can only do single inheritance. You can't do multiple inheritance. Extends only accepts one parent class and nothing else. If you try and add more, it's a syntax error. The other concept we're going to have a look at is abstract classes. That should be first on the agenda. So we'll look at that first, and then we'll look at interfaces as a way to solve the diamond problem. So with abstract classes, you know them in C++ as pure virtual classes, classes that have only pure virtual functions. What is a pure virtual function? Anyone? Pure virtual function in C++? So it's a function that has to be overridden, but what it actually says is a function that has no definition. It has a declaration, you have the name of the function, you have the return text, you have the parameters, but there's no implementation of the actual function. Where do we find the implementation? In any derived classes. In the derived classes, you are forced to implement it unless you make it virtual again. Then your child classes will need to instantiate that specific method. So in Java, we have the similar concept with abstract classes. Instead of having pure virtual functions, we have abstract functions. Abstract functions, abstract methods, they also define something that is going to be implemented by child classes, not necessarily the current class that we are working in. So why do we need abstract classes? Why do we need classes that contain abstract methods? So if we look at the inheritance hierarchy and we look at going up the hierarchy, as we go up the hierarchy, what happens? We get less specialized, less information that is required. And as we go down the hierarchy, we get more specialized. We have more things that are unique to the things that are low down the hierarchy. So at some point in time, in the problem domain that you're working in, it doesn't make sense to make an instance of something that's higher up in the hierarchy. So one example that we'll have a look at, and that's the example that we usually see in the slides, is to do with shapes. So we looked at the shapes in the previous lecture where we looked at geometric objects, and we had a rectangle and we had a circle. So a rectangle, you know what that looks like. A circle, you know what that looks like. What does a geometric object look like? So geometric object is another name for shape. What does a shape look like? Well, it depends on the type of shape. What is an area of a shape? Depends on the type of shape. What is the perimeter of a shape? Depends on the type of shape. So we can't create an instance of geometric object. It doesn't make sense to. So we can define that as an abstract class. We can say that whichever class implements or inherits from us needs to implement something like area, something like perimeter, maybe a method for printing. So we can force our child classes to provide their functionality because it doesn't make sense in our parent class to do so. So abstract classes are for classes where you need to store that information, but in the context of your problem domain, which doesn't make sense to create an instance of that. If we look at our tutorials that we're going through, and we look at the person class we created, does it make sense to create a person in the context of our problem domain? Person has no meaning. It doesn't serve a purpose in our problem domain. But we can use the subclasses, lecturer and student, and they do make sense. So when we get back to tutorials, we're going to change that person class to be abstract because it doesn't make sense to create that an instance of that specific class. So with abstract classes in Java, there's some interesting things that happen. Abstract, there's an abstract keyword that you use at the top of class to indicate that it's abstract. We'll see that when we get to code. We should get to code today if we go through the slides fine. And a class can be declared abstract without having any abstract methods. You can have a mix of abstract methods, so pure virtual functions if you look back in C++, and functions that have implementation. You can mix both. But as soon as you have an abstract method, you have to have an abstract class, but it's not true the other way around. An abstract class can have no methods, and it can have no abstract methods, but some other implemented methods. Abstract classes can have constructors. Constructors are used to initialize the state of an object, so that can still exist. We can't call those constructors by themselves. We can't create an instance of an abstract class, but through the use of a child class that implements that, extends that specific abstract class, we can then get the functionality through a superconstructor. So we can initialize the values through a superconstructor, even though we can't create one inside normal code. A parent class, a subclass can be abstract if the parent class is concrete. So concrete basically is the antonym of abstract. It's a class that has implementation. And this has to be true because every class has an ancestor class called object. An object is not an abstract class. So it has to be true for this to work. You can have a subclass that is abstract when your parent class is concrete, and that chain can continue. You can have a subclass that's concrete again, then a subclass that will be abstract again. The hierarchy doesn't really matter as long as you conform to having those specific things inside of the abstract class. You can create references to abstract classes. So I can declare a variable of type whatever the abstract class is, so person or geometric object. I can't create an instance of it, but I can create a reference of it. So just like we did yesterday in the practical lecture, we create references of person. And we put students inside of there, put lecturer inside of there. We created a reference. Creating a reference is perfectly fine. Instantiating an abstract class, that's where you're going to have a problem. And then the last two points, abstract methods cannot be static. Static belongs to a class. It doesn't make sense to have an abstract static thing because you can't override static methods. So abstract methods cannot be static. Abstract methods cannot be contained in concrete classes. As soon as you have an abstract method, the class is then abstract. If you leave out the keyword, the code won't compile. Now I move on to interfaces. So with interfaces, they are a class-like construct. Because we're trying to solve the problem of multiple inheritance, we need something that looks like a class, but doesn't provide the same functionality as a class. So what an interface does, it provides abstract methods, and that's all. It does not have state, and it does not have implementation of anything. It just provides methods that anything implements. So that's a new keyword we're going to use. We're going to see the keyword implements. You have to provide functionality for those specific methods. Unless you abstract, then your child classes have to provide that implementation. So interfaces, you can have more than one. Parent class, you can only have one. Interfaces, you can realize, that's the keyword that we, or the word that we use when we talk about inherit the relationship. It's realize multiple interfaces. So you inherit one parent class, but you can realize multiple interfaces. And because you can realize multiple interfaces, you can sort of implement the same functionality as you would with multiple inheritance. Not exactly the same, but very similar. So interfaces are usually used to group a set of shared behaviors between unrelated classes. So what does that mean? It means that you can provide functionality to something that is unrelated, but there is something common between them. An example, we talked about our inheritance hierarchy between, or not having a hierarchy between a rectangle and a person. Even though both of them had a width and height, we didn't want to put them in the same hierarchy because it didn't make sense. But there could be a situation where we're creating rectangles of a certain size, and we need a person to match the size of that rectangle, and we want to compare the sizes. Now that seems very abstract. When would you compare rectangles and people? Well, if you have a camera looking at a crowd, and you need to put a box around a person to identify, here's one person, here's another person, here's another person, then you have a situation where the box outline matches the person's outline, at least as close as possible. So then you need a way to compare this box and this box, which represent the people inside of those boxes. So that's one situation where you could potentially do something like that. Another place, it might be that you are comparing different things that might have a cost. Even though the things aren't related, you might be comparing a car with an apple. Even though the things are unrelated in the hierarchy, they still have a cost associated with them, and you might want to compare the costs. So there has to be a way to do that without interfering with the functionality of the class, without putting extra things into the class that doesn't need to be there. And we do that through interfaces. Now, there is some things inside of Java that happen since version 1.8 or Java 8. And one of those things are default methods. So right at the bottom of the slide, you'll see there's a comment there about default methods. So default methods provide a default implementation, even though I said interfaces don't have default implementation. So this was a new thing. We're going to ignore that. It's there, but we're going to ignore it. We're not going to be using this. And the reason for that is so that you can better understand the point of interfaces. So just like you'll see with other things later in the semester, there's some things we'll talk about, but we're not going to use because obviously I can't show you everything, but I'll point you that this exists. You want to find more information about default methods? Textbook is a good resource for that. And speaking about the textbook, a lot of students come up to me and ask me for more examples. The examples I'm giving you are the more examples, more than what is provided in the textbook. Remember, this course does have a textbook, and that's where you find extra information. The slides that I'm showing you right now, that's my summary of the textbook that I'm showing to you. When you're studying, you should do your own summary of the textbook in preparation for your tests next week. Okay, so a comparison between abstract classes and interfaces, because sometimes people get confused between the two, so just to clarify what's the differences between them. So you can see that instance methods are allowed in abstract classes because I can create instances of my child classes, so I can have instance methods there, instance variable as well. I can have instance variables, but in abstract classes they allow, in interfaces they're not allowed. There's no state that can be stored in an interface. You can have constants, so static final things declared in an interface, but you cannot have instance variables declared in an interface. You can extend only one class, but you can realize multiple interfaces. And the relationship with abstract classes is the same as any other class. It's still an is a relationship. The wording for an interface is a bit different. It's called is kind of. So that's the notation that you would use when you talk about the type of relationship. And that same naming convention is used in the slides in documentation, which we did a while back in the practical lectures, that show you how to do is kind of, or the interface realization inside of UML. We'll see an example on the next slide. So here is what we've seen already in the last lecture, where we looked at geometric object, circle, and a rectangle. However, you can see now at the top of the geometric object class, there's in angle brackets, which is sort of an annotation for UML. You can see there's the word abstract. This is to indicate this is an abstract class. Then if you look at the rest of the stuff, it looks very similar, except inside of geometric object, we now have get area and get perimeter. And how you should indicate that they are abstract methods is put them in italics. So it might not be so clear on the sides, but it is different to, for example, how the constructor looks. And that's to show that that is an abstract method. There is another syntax where you can put the abstract with the angle brackets next to your return type there, but that gets very cluttered very quickly. So that's the preferred method where you put italics for abstract methods. So if you look at our geometric object class, you can see now there's a abstract keyword there. And then abstract keyword just indicates that this class is now abstract. And then the rest of the class looks the same as we've seen before. We still have our color value, we still have our filled value, date created value, our toString, and then right to the bottom, that's where we have our two extra methods. And both of those are declared as abstract. So just as the example I was talking about earlier, geometric objects do have an area and a perimeter, but it doesn't make sense to do it inside of our abstract class because we don't know what the area of a geometric object is. We have to look at the subclasses to get the information. Therefore, we declare it as abstract. And you can see there's no curly braces indicating the body of the method. It's just a semicolon. When you did this in C++, you had the method signature equals 0. Do you remember that? Method signature equals 0. That indicates there's no implementation. So it's very similar here. With abstract keyword, we're indicating there's no implementation, but our child classes have to provide that implementation. So the rest of the classes, they already had the get perimeter and get area from the previous one, so I'm not going to re-show that code. There's nothing different in there. There's literally no difference in those two classes. The only thing that changed was your abstract class. And we'll see this when we do the person class in just a moment. Now we're going to have a look at an interface that we're going to work with geometric object. So here you can see the UML for a simplified view of that geometric object class. So not the rest of the information because it's not relevant. But there you can see there's a dashed line with an arrowhead as opposed to solid line with an arrowhead. So solid line arrowhead pointing to the parent class, that indicates inheritance. Dashed line with an arrowhead indicates realization, implements an interface. And there again, you can see interface with those angled brackets, indicating that this is an interface. And there's our one method again with that italics to indicate that it's an abstract method. You don't have to put an abstract keyword when you do an interface. You don't have to indicate abstract because any method inside of there is abstract by default. And usually you specify what parameters, what return types of the method signature you define in your interface. Because geometric object is an abstract class, it doesn't have to implement that method. The child classes will implement that method. This is just indicating that somewhere in the hierarchy, when there is a concrete class, they have to implement a compare to method. So what does this compare to method do? We've seen compare to before. What does compare to do? Lexicographic ordering of two objects. That's using strings. If you compare two strings, it does lexicographic ordering. If you compare two objects, you can see that it returns an integer. So if the current instance is behind the parameter, it returns a negative number. If they are the same, it returns a 0. If it goes after, it returns a 1. So that's the general concept behind it. How do you get to those numbers? It depends what you're comparing. It depends what you're comparing. If you look at the parameter, what is it? Object. You can compare anything, any reference. How you define that depends on your implementation.
So with this as object, why would you choose to pass integer instead of passing anything else, such as enumeration or Boolean?
It returns an integer. It's when you sort something, usually you sort on numerical position.
So comparing its position in one
Not in the heap, in whatever implementation you want. So if you have an array of random things and you want to sort it, how do they sort it? They compare one instance to the next instance, and then you swap it until you get an ordered sequence. We'll see now in the compare to method, when in our implementation, we'll define how that works. If you have a random set of references, some might be strings, some might be students, some might be geometric objects, you can compare them if you define comparisons. If you don't define a comparison, it will use the default implementation if you can find one, and that will usually use the hash code. So here we're going to provide in the geometric object some implementation. We can't change this in the child classes, but here we can provide some implementation, and we're going to leverage the fact that we have area as something the child classes will implement. Remember, the geometric object doesn't have implementation for area. It doesn't know how to calculate area. But a circle does, and a rectangle does. So if you look at the code, you can see obviously this is inside of the geometric object class. There's obviously other things before this, but this is we're looking at that specific method. And in there you can see compared to the other object, and let's go back to line 1 first. Implements comparable. That's implementing our interface. Then on line 5, the first thing we do is we check, is our parameter an instance of geometric object? If it's not, if it's a string, if it's an array, if it's a person, if it's a student, it's whatever else, if it's not in a geometric object or a subclass of geometric object, we just return 1. We go after. That's all we indicate. You could return -1, that's also fine. You can't return 0 because we're not equal to that thing, so we don't return 0. So after line 5, anything that comes in the parameter should be a geometric object. And we can change this implementation as needed because we have something else we can also compare, but we'll talk about that in just a moment. So line 7, we convert our parameter to a geometric object, and then we compare our areas. If our area is greater than the other area, we can return 1. If our area is less than the other area, we can return -1. Otherwise, if those two if statements go through, that means the areas are equal, we can return 0. And this is because every geometric object has to implement area. You have to have a value for that. What other method did we have available that we could use? What other method do we have available? Parameter. So every subclass has to implement area, and then every subclass has to implement parameter. So if you really wanted to, you can compare first the areas. If the areas are equal, then we can compare parameters. And only if the areas and the parameters are equal, then we can return 0. So you can extend the functionality of what's happening here a lot more. If you want to compare person inside of here, you can instead change that code and say, if it's not an instance of geometric object, you can say if it's not an instance of geometric object and it's not an instance of person, then you can return 1 and then write code that will handle person, write code that will handle geometric object. Now, obviously, you need access to those classes if you want to implement something extra in here. Remember, there are no friend functions here, so we can't add functionality like that. You have to have a way to import that class if you want to use it inside of this compare to. Okay, so that's it for the lecture portion. So we're going to have a quick look at some code. So what we said we're going to do is, with our person class, it doesn't make sense to instantiate instances of our person class. So we can make it abstract. But as soon as we do that, student class works perfectly fine, no problem here. Lecture class works perfectly fine, no problem here. But in our main, we had a situation where we created an instance of person, and now that is no longer possible. So I can't create an instance of person. But I can still create a reference to person. So I can still create a variable called person, of type person. I can put stuff inside of there that fits in the hierarchy of person, but I can't create instances of person. So let's implement an interface, and we can implement comparable, and you might see something extra appear there. You might just remember this notation from C++, templates, angle brackets. So we haven't learned that, so we're just going to ignore that for now. We'll complain, but yeah, we don't need to do that right now. But what this interface provides, there you can see an interface, public interface comparable. We'll ignore that T for now. and it just provides a compare to, returning an integer. And then it gives you a rundown of how compare to actually works. Now, because we implemented this interface in an abstract class, the abstract class is perfectly fine. However, if we look at student, the student class will no longer compile because we have to implement this specific method. Parent class is abstract, doesn't need to implement the method. Child class is concrete, we have to implement all abstract methods. So here we have to implement this abstract method. And that method is compare to with object. And again, you can see there's the at override annotation to indicate overriding the functionality of this thing. And there we can compare things that are of type object. Now, if it's of type object, we don't know what it is. It could be a string, it could be a module, it could be a degree, it could be a geometric object, could be any number of things. In this class, what do we care about? In the student class, what do we care about? Student, nothing else. So we have to do a check. So if we're not an instance of student, we bigger than it, we go after them. Otherwise, what we can do is then compare something that's unique to the student. We said that names, first name, middle name, last name, they're not unique. We can't rely on that. What is unique is the student number. That is unique. So in our case here, because we have integer student numbers, we can do something like okay, so first I need to convert that parameter to a student. I don't need to use the accessor method. I can use field directly. And that will return a number, -0 if it's the same, or positive. If it was a string, you could do something similar. So just let's say, for example, instead of this, we want to do with strings. Yeah. So because this is first name is in my parent class, and my parent class declared first name as private, I have to use an accessor method here. So here I'm doing comparison between two strings, but I don't need to worry about how strings are compared because string has its own compare to. So I rely on the strings compared to do the final comparison. I can take this further and say, okay, if this compared to returns 0, let me compare to middle names. If the middle names return 0, let me compare last names. If the last names return 0, then I can return 0. You can extend the functionality to compare everything in the class. But because we said that student numbers should be unique. We can just compare based on student numbers. So now when we sort, the sorting algorithm will implicitly call compare to and then arrange students according to student number. If you didn't have this compare to, it would use whatever information it has available, and that would be something like the hash code, and just do it that way. So interfaces, you will be creating your own. So this comparable interface is something that is built into the language. Let's get rid of this window. You can see it's inside of the Java lang package, so it's built into the language. But you'll be writing your own interfaces very soon as well. When we get to the next big thing after graphical user interfaces, when we get to design patterns work on the principle of interfaces. Interfaces are everywhere. So there you'll see a lot of interfaces and a lot of examples that use interfaces. But we still have a lot of things to get through before then. We still have to do binary files. We still have to do generics. We still have to do graphical user interfaces. So lots of things still to come. However, at this point in time, we've covered all the content that is required for your semester test. So that's everything that you need for your semester test until lecture 7, up to and including practical 2. So practical 3's content does cover some of the stuff, but because you don't have the memo for that, because it's only going to be due after the semester test, practical 2's content will be potentially in your semester test as well as any code that you see in the slides can also pop up in the semester test. As far as the breakdown is concerned, I'm going to spend tomorrow discussing the breakdown of your semester test, so I'll tell you what it's going to look like. Unfortunately, it's not going to look like any other test that you've seen before. So I will be giving you past papers. I'm going to see if I can give you 2 past papers. One of them will be the last year's past paper, and one of them will be pre-COVID past paper. And the reason why that has to be done is because last year and 2020, it was open book online tests. Pre-COVID, it was not open book written tests. And that's where we are right now, not open book written tests. So there is a little bit of a change in terms of what happened in the previous 2 years. We're going back to sort of what we used to do before. So those details I'll talk about in the actual tomorrow when we get through going through a past paper. See a question? Is an abstract class limited to only one interface? No, I can have as many as I want. I don't have any interfaces that I can think of off the top of my head to implement, but you can have more than one. So what you can do is inside an IDE, usually if you type the keyword extends, okay, maybe not for extends, let's get rid of that. With interfaces, usually you'll see there's a specific symbol that is represented for an interface. It's an I. Per class, you'll see C. For an enum, you'll see E. In Eclipse, it will be different colors as well. And this color is also present in inside of the outline here. You can see there the module is a class, therefore it has a C there. If you go to person, you can see person with an A there. So here, when I'm asking the IDE to help me out with certain things, you can see here's a whole bunch of different interfaces that you can implement. Now, some of these won't make sense, but there you can implement that interface. So you can implement more than one, but that means your child classes now will have a situation where they must implement whatever things are in that interface. We can write our own. So if we want to, we can put an interface here, new. So one way you can do new classes and new things inside of an IDE, right-click, new interface, give the name of the interface. Okay. So there's my interface, and I can leave it blank. There is a concept of having blank interfaces, and that's called a marker interface. We'll talk about that when we get to GUI interfaces. So here I can have a method. Everything is declared as public. So here's a method that needs to get implemented from this interface. I can put this into my person class. And note the convention is to, if it's an interface, put an I. Some of the older Java classes didn't do that, but the new ones do. They can't change it for backwards compatibility reasons, but that's the convention you follow. Enums have an E, interfaces have an I. Classes should have a C, but that seems to not be in favor at the moment. So there I have this interface being implemented in my abstract class, but my student class doesn't have the implementation, so it will complain I need to provide that specific implementation. So you can add this method now to this class. And similarly, we'll need to add this to lecture as well, because remember, that's also a subclass that we need to implement. So now we have that implementation available. And we can go inside of our main, for example, and if you look at these person instances, check out our other print lines here. So our person references that we have here, P2, we can now call test on them, because the person class implements those interfaces. It's publicly available. It says it's there. We can do compare to as well. So we can say compare to the two person things that they are there. But because P2, if you look at P2, P2 is actually a student reference. So it will do the students compare to. And that will give us the answer for comparison with a student and something. If we do it the other way around and we say EL compared to P2, that will show the implementation of the lecturers compared to. So you can have more interfaces if need be. So you can have a long list if you really want to. Okay, so that's the end of the session. If there are any questions, I'll be here for a few minutes. Otherwise, I'll see you tomorrow.